I will talk about high-fidelity nano-FTIR spectroscopy. And it's a very cryptic title, but we looked this up in a dictionary. And it means high-fidelity means high accuracy, high reproducibility. Let me just open this. All right, OK. So high accuracy, high reproducibility, this is what we want to achieve. And in this talk, I will briefly recap what are we actually measuring in the s-SNOM. I will talk about the role of near-field and far-field reflections in this. Then I will give an example of a background-free signal. But as you can see here, as a preview, the signal will not be flat, even though the sample is homogeneous. But by using ratios of different signals, we can achieve much higher accuracy, and now the signal will be flat. And then I will talk about other applications of this method. So as mentioned in the morning, we basically can probe with s-SNOM either electric fields, as for example here for mapping near-field distributions of antennas, or for mapping polaritons. Or the other branch of the community, they are doing chemical analysis. For example, you record nano-FTIR spectra to tell which material is which. And in single-frequency imaging, you can then take a map of where is that material. But what's here on the slides is nicely separated. In reality, it's not separated at all, because you always probe both of the things at the same time. And for this, let me show you this example. We've seen it before from Rainer's group. If I just plot here a bit longer frequency range, what you can see here is we do have, again, this curved lines. They are coming from the polariton response, so they're electric fields. But here, this frequency-independent or this position-independent line is actually the dielectric response of the flake. So it's clearly we measure both effects at the same time. It's a mixed response. But this is often overlooked when doing this type of experiments. So I will talk about this now. And essentially, what we're all probing is the tip scattered field. And just here, as a very simple equation, we have this effective polarizability of the tip, which depends on the near-field reflection coefficient. But also, we have the incident field that's incident on the tip. So we also is proportional to the scattered field. And now this incident field, it depends also on the sample. Because we illuminate the tip not only directly, as shown here, but also via reflection at the sample surface. So that means we somehow have this far-field reflection information on our tip. So in the equation, we have this 1 plus r squared to describe this. And this is now the far-field reflection coefficient. It's different from the near-field reflection coefficient. It's very important that they are different. And for example, here, the near-field reflection coefficient, essentially, we are probing a nanoscale spot, in this case, the material C. But the far-field reflection is coming from a diffraction-limited area. And in this case, we would probe materials B and C. So that's why we should consider far-field effects. But we're not really measuring the electric field, but we're measuring a demodulated signal. And then making even one step more, we're measuring a demodulated signal referenced to a reference material. So really what we are analyzing normally is something like this. So the near-field scattering coefficient at a certain demodulation order n is described by this term. So it has a far-field part and a near-field part. And it doesn't matter how much you demodulate the signal, the far-field part will always be there. But that doesn't mean it's always relevant. So here are depicted some cases where the R sample is the same as the RF, and then they will cancel. So if you have a small nano object, like a virus on a substrate, and you also normalize to the substrate, the far-field contribution will cancel, so you don't have to worry about this. The same is if you're at a microstructure measuring near the edge, but you illuminate the tip via the substrate, again, far-field doesn't matter. If you have a very thin film, the far-field reflection is almost the same as in the reference, so they will also cancel. But in many cases, especially more applied samples, maybe you have a nano object in a crowded environment, you don't even know what is the far-field reflection coefficient. You have no way to really measure this or to calculate this also. The same is if you're on the inside of a microstructure You have some part coming from the film that's reflected to the tip, some part by the substrate. So it's getting very complicated. But don't worry about it, we can make it more simple. So here is the example from the beginning, where it's just a gold patch on calcium fluoride, and the gold is homogeneous. We would expect a homogeneous signal. We see that for low demodulation orders, there's a lot of background light. We can remove it by demodulating, but still the signal is not flat. And this is what's happening here is we have, for example, in the center of the gold, we have near field reflection of 1, far field reflection of 1, so it's very large. But near the edge, the near field reflection is the same as 1, but far field is now basically 0. So that's why we have here a smaller signal at the edge compared to the middle. Now the situation is a bit more complicated because we also have scattered light from the edge, they interfere. But now the very nice thing is, and this is the most important part of the talk, all of these illumination, far field illumination effects, they are the same, independent of which demodulation order you look at. So if you just divide the two, then all this will disappear. And we made it for this data, and indeed, all these effects are gone. We don't have to describe them. And it's important to take always the complex valued ratio, so amplitude and phase. Here it's shown for images. We can do the same also for spectra. This is now shown here. It's a very full slide. But essentially, what we did, we placed the bornitride flake on silicon. And we did this because bornitride has very high reflection, but only around 1400 wave numbers. So if we measure here on silicon, and also normalize the silicon, so it should be flat, we see that the amplitude here is indeed increased. And this is coming from this indirect illumination via the bornitride flake. And yeah, it depends on how far away we are from the flake, but we can still see it up to 10 micrometer in this case. But as before, nicely we can just remove it, divide the two signal channels, all the problems disappear. But now the interesting question is what happens with the near field? Maybe it also disappears. So this is why we made another experiment on TMVs. Now we just saw it in the talk before. But we made here as a controlled experiment, we designed the sample in a way that we have a pure far field response, just like on the slide before. So we're probing only this indirect illumination via the HBN. We see again this peak in the nano-FTIR spectrum, which disappears when calculating the ratio. Now, if we have a pure near field response, that means we illuminate via the substrate, we see the real spectrum of the TMV, which is just M81, M82 bands in this case. And very nicely, when calculating the ratio, the spectra looks the same. So the peaks are the same, the shape is the same in amplitude and phase. So we can interpret them analogously to the nano-FTIR spectra. Now I have to admit the contrast is a bit reduced. That's the drawback of the technique. You lose some contrast, but you get more pure near fields. And now putting these two cases together, essentially, we have near field response from TMV, far field response from the HBN. We would get in the phase here 3 peaks, for example, and if you compare this now with the infrared spectral database, what is it going to tell you what material you have below your tip? It's going to be wrong, because you don't have this peak below your, this material below your tip, you have only the TMV. You take the ratio, and then exactly you get what you would expect normally from a nano-FTIR spectrum. Yeah, so this is the main idea of the paper that I'm presenting. But you can do other things with this ratio, so just dividing signals of different demodulation orders. Yeah, so like Alex and Dimitri have shown, they did it before to remove far field effects. Fritz and Corbinian, they have shown maybe you don't have to normalize your material to a reference material, just normalize to a different demodulation order. Then in another work, we've shown this ratio can give you more information about the depth of an object, if something's on the surface or maybe below. This is actually a very interesting point. Very often you can observe a tilted baseline in nano-FTIR phase spectra, which is caused by interferometer drift. But this drift is the same for all demodulation orders. So you divide them, you get rid of this drift completely. If you have fluctuations in the laser power, actually by chance, during this scan, the laser lost its power. Normally what you would do, okay, you measure again after retuning the laser. But if you calculate the ratio, actually you can use the data still. And surprisingly, this contrast is not affected at all by the power that you have. And then maybe a special application of this effect is if you have, if your optical signal is modified by mechanical vibrations, like in a cryo system, for example. You can suppress them, maybe not fully remove them, but suppress them also by calculating such a ratio. So it's a lot of possible things you can do this. And it's very easy to make, because when you measure, you get different emulation orders at the same time. So I recommend just, if you have some data which you don't understand, calculate this ratio, see what happens. Maybe it will help you. Okay, I have 1 more minute, I think. And this illumination effect is not specific to s-SNOM, because we made a sample, a 2-component polymer sample with a big scatterer of just silver paint, and illuminate via the silver paint to create artifacts. We can see here in the top right corner, the signal varies a lot. This is caused by the indirect illumination, but we can remove it using the ratio. But here on the right slide is shown also for tapping AFMIR that we also see a big variation in the contrast, which I think has not even been reported yet. So maybe there will be more studies on this in the future. And with this, I would like to summarize. We've seen we measure near field and far field in the SNOM, but we can get rid of the far field by using the harmonics ratio. Thank you to everyone at Nanogune for helping with this, and to you for your attention.